Picking up on page 26 in the notes, but first I'm just going to talk about refraction like you talked about it in grade 8, okay? That's honestly that level of understanding of it. I mean, we're going to have to do more math, but you actually learned in grade 8 pretty well how refraction works, okay? Now, whether or not you remember that is a different thing, but I just want you to know, don't be scared by this stuff because you're experts, or you were at one point, okay? So refraction is just when light bends because it's passing from one substance into another. Why? Because light travels at different speeds in different substances. So some of you right now are freaking out and saying, hey, the speed of light is a constant. The speed of light in a vacuum is constant, okay? The speed of light will change in different media, okay? Media being the plural of medium, okay? So the analogy that I think of when I'm trying to remember how it will bend, okay, is a truck going into mud. So imagine a truck from above going into mud, okay? So it needs to enter at an angle to get bent. But if you imagine this truck entering some mud, okay, at an angle, so the truck can go faster here on the dry pavement, but it will go slower here in the mud. So as it comes in, okay, that front right tire is going to hit the mud first. And so what's going to happen is that tire is going to get slowed down. It's kind of going to spin and drag, right? And so it will bend a little bit that way, right? So the light gets bent a little bit that way. Notice there, it's been bent a little bit, okay, from its original path. Okay, so that's essentially what we have here. We have light entering, okay, air where it travels very close to its speed in a vacuum, and then entering glass where it gets slowed down. So notice if we drew the normal there, okay, it bent towards the normal, right? If this is the normal, it got bent towards the normal. Okay, so we can visualize it again here with the truck, right? And the glass can be the mud because guess what? Light travels slower in glass than it does in air, just like a truck in mud. So as it comes in along that path, notice, okay, the tire hits and it gets slowed down there first, or in reality, the wave front, okay, but we can use the truck analogy for now. And then it travels along the new path. And then guess what? Light bends when it speeds up too, okay? So the same way the truck would speed up. So as that front wheel now leaves, okay, now it's on dry pavement. So that side gets a bit faster, and now it bends that way. Okay, so it gets bent that way from its original path. So again, we can picture it here. Why did it bend that way? Because that front right tire hit first. It started moving faster and making the truck spin until, there we go. Okay, so that is a good analogy. Let's kind of look at real stuff. Okay, so light moves faster in air. It actually moves pretty close to its vacuum speed. It slows down a little bit in air compared to in a vacuum. Okay, it moves much slower in glass. That's why we use glass to bend light. That's why your glasses are made of, well, glass. Okay, and then we have air on the other side. So let's take a look at what happens. Okay, so we have the normal, just like we did with our law of reflection. Okay, that's still called our incident ray. Our normal is going to be there. Okay, what do you think that angle is called? Still the angle of incidence, right? Still the angle of incidence, okay, because it's the angle between the incident ray and the normal. And then that light is going to get slowed down, right? So I think of it as the light. I imagine in my head whenever I do refraction, I imagine that I sort of think of the normal as like having gravity or something. And if the light gets slowed down, it will kind of get pulled back towards the normal's gravity. But if it gets a speed boost, it will get away from the normal. Okay. So whenever light gets slowed down, it bends towards the normal. Okay. So this we call our refracted ray, and we would call that the angle of refraction. So when light gets slowed down, the angle of refraction is smaller than the angle of incidence. Okay. But now look at what's happening here, right? Now we have light exiting the glass and entering the air. So we have another kind of surface here, right? We have another transition between media. So now it's going from glass to air. We draw a new normal, okay? And now this old refracted ray could be our new incident ray. And so we have our angle of incidence, okay, our new angle of incidence, and our new refracted rate. So now it's going to go faster. So I think of it, okay, it got a speed boost. It's going faster. Now it can get away from that normal. I think of the normal as trying to suck it in. And if it gets a speed boost, the light will succeed in getting away. But if it gets slowed down, it will kind of get sucked in by the normal a little bit. Not what's happening at all, but it helps me remember how to do it. Okay, so that's our new refracted ray. And that's our next angle of refraction. If light enters a medium where it can move faster, the angle of refraction will be bigger than the angle of incidence, right? So first angle of incidence, first angle of refraction, because it got slowed down, the first angle of refraction is smaller than the first angle of incidence. But then our new angle of incidence, right, is smaller than our new angle of refraction because it sped up when it went from glass back into air. Okay, and just to visualize this on the real picture, right, we draw our normal in. Notice air to glass, so the angle got smaller from incidence to refracted. Okay, and then glass to air. So now the angle of refraction will get bigger. It will bend away from the normal. Okay, so just kind of a summary here. When a substance makes light slow down, the angle of refraction is smaller than the angle of incidence. When a substance makes light speed up, the angle of refraction is larger than the angle of incidence. In other words, when a substance makes light slow down, it bends towards the normal, but when it makes light speed up, it bends away from the normal. Okay, so what makes light slow down? Well, it depends what it's coming from. So we have this idea called the refractive index. Okay, essentially what this number means is how much does this thing slow light down? So you can see in a vacuum, the refractive index is 1. Air is 1.000. Actually, I believe it's more like 1.0003. On your formula sheet, it's actually even given as 1.00. So use that unless the question says something else. Okay, how do you interpret these numbers? Well, water's refractive index being 1.33 means that light will travel 1.33 times slower in water than it would in a vacuum, right? So to find its speed, basically divide by that number. So for example, if light goes from air to glass, it slows down and therefore bends towards the normal, right? But if it goes from, let's say, glass now to water, water has a lower refractive index, so it's going to speed up and it's going to bend away from the normal. So here's a classic example, okay? Because refraction messes with how we see stuff. So where will you see the fish? Well, a ray of light could leave from there. Okay, let's say I just picked one. Hit the normal. Now it's going from water to air. So is it going to speed up or slow down? It's going to speed up. So will it bend towards the normal or away? Away to your eye, right? That's why it hit your eye. Otherwise, that ray wasn't destined for your eye. So you will trace that back and you will see the fish there. Okay, where will the fish see you though? So light will leave your nice blue hat. It will hit the water from the air. Will it speed up or slow down? It will slow down because water has a higher refractive index, right? So we draw the normal. We're slowing down, so we get bent towards it. And if the fish's eye traces that back, they see you much closer to you than they are. So again, guys, that was actually the exact slideshow I used when I student taught Science 8 back in university. Okay, so just saying that to comfort you and say, hey, you've done this before. The main idea is you've done before. Okay, now we're going to have obviously do a little more with it, a little more math and a little deeper understanding of it. But the general idea of refraction, you have actually seen. So refraction is the bending of light as it travels through a different medium. When a wave enters an optically denser medium, usually that does just mean denser. Like usually optically denser and denser end up being the same thing, but technically it's different. It just means when light has a harder time traveling through it. Speed, wavelength, and refracted angle to the normal all decrease, while here's the kicker, okay? Frequency is constant. You need to remember that always. When light gets refracted, frequency does not change. Okay, so the amount of change is directly related to the index of refraction. You can think again of the index of refraction it's unique to a whole bunch of kinds of materials, okay? And it essentially means how much slower does light travel in this substance compared to in a vacuum. Okay, there's a whole bunch of common indices of refraction in table 13.4 on page 667. The wave model here, remember you learned in physics 20 that waves refract, okay? So the reason is that as the wave front kind of enters, right, it gets slowed down, just like the truck in mud, right? It kind of gets slowed down, and as the rest comes, it kind of bends as it catches up. So just coming back to the idea now of frequency staying constant. So frequency stays constant. Let's think about it. We have V equals F times lambda. Okay, now we know V is changing. That's why this thing is refracting. So if the frequency is going to stay the same and V is, let's say, slowing down, well, then lambda must also get smaller, right? Otherwise, those two things are not equal anymore. Okay, we can either maybe make it a bit more obvious by solving for F, right? If this number needs to stay the same and let's just say we're now dividing by a smaller number, well, then we need to have a smaller number up here too. Otherwise, frequency would get bigger. So if let's say it's entering some substance, Okay, if light enters some substance, we'll have some big wavelength, and then maybe if it's getting slowed down, the wavelength will get shorter, okay, but the frequency will stay the same. So V down, wavelength down, frequency the same, okay? So a trick that helps me remember this, okay, it helps me visualize what's going on. Think of ticker tape. So remember ticker tape, how does it work? It ticks at a constant frequency. It goes tick, 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 tick. If you make it move faster, the dots spread out. So the dots are like the crests of the wave, right? As you make it go faster, the dots spread out more. But if you slow it down, it still just tick, tick, ticking at the same frequency it always has been, but the dots get closer together, right? So ticker tape is kind of a good analogy to wrap your head around what's happening. It's always frequency is the same. It's always tick, tick, ticking. But if you speed it up, the dots spread out, the wavelength gets bigger. If you slow it down, the dots get closer together. The wavelength gets smaller. Okay? I know what you're thinking. If the wavelength changes, does the color change? No. Frequency is actually what determines color. So I know I told you, think about the wavelengths to think about the type of EMR. That's true. That still kind of works, honestly, always. But the thing is that but truthfully, the color does not change when the wavelength changes because the frequency is ultimately what determines color. In a vacuum, though, it will usually be when you are thinking about that kind of stuff. So you won't have to worry about that. Okay, so Snell's law. N is equal to sine theta 1 over sine theta 2. So this is the angle of incidence, and this is the angle of refraction. These, of course, are the speed in medium 1 and the speed in medium 2, the wavelength in medium 1 and the wavelength in medium 2. I should say sine of and sine of angle of refraction, right? It's not the angle and the angle, it's the sine of the angle and the sine of the angle. Okay, you can derive these and you will in your first year university courses, but I won't bother with that right now. Notice with all of these that the change that's going to happen to the variable, so example, what's going to happen, how is our angle going to change is just saying what is sine theta 2 going to be, right? How is V going to change is saying what is V2. How is wavelength going to change is saying what is wavelength 2. If you solve all of these for the 2, notice that in all of them, okay, you would end up having n being divided, right? So whatever it is, whatever variable blank 2, okay, gets smaller as n gets bigger. So the more light gets slowed down by the medium, n, right, the smaller the wavelength's going to be. The more it gets slow, well, obviously, the more it gets slowed down, the slower it's going to go. And the more it gets slowed down, the smaller the refracted angle is going to be. Okay. Now, careful, that doesn't mean it refracts less. That actually means it refracts more, right? Because that means it bends further towards the normal, assuming we're talking slowing down here. Okay. Now, important note for later. Okay. It's going to come up in the next topic more, but still. Shorter wavelengths bend more. So blue bends more than red. Okay. Blue has a shorter wavelength in the visible spectrum. So that's going to be important later when we look at dispersion. Okay. Just pointing it out for now. It says that n equals 1 for light in air. It's true definitely for a vacuum. Technically for air, it's 1.0003. But even on your data sheet, it says 1.00. So use that unless question says different. Okay, unless the question says use n equals whatever. They'll have to tell you that. So for an example, light enters salt water and slows down to 2.22 times 10 to the 8 meters per second. So light enters salt water, I'm just going to add from air. Okay, it slows down to 2.22 times 10 to the 8 meters per second. What is the index of refraction of water? So we have that n equals V1 over V2, right? Which equals, it was in air, so 3 times 10 to the 8 meters per second over V2. 2.22 times 10 to the 8 meters per second. So I got, and that's pretty close to the value in your book, 1.35. Okay. Realistically, this form is helpful, but most of the time you're going to end up using this called the modified Snell's law, which just takes all of those relationships and puts them into one nice handy dandy form. So it just takes all those relationships and puts them into one big thing so that you can pick and choose, right? If the question asks you about this, you can say that and that, or that and that, whatever. So let's go do a couple examples. So red light has a wavelength of 650 nanometers. This wave is moving, I'm gonna add again, through air. Should have had that in there, sorry. Okay, So this is going to be lambda 1. This way is moving at an angle of incidence of 13 degrees. So that is theta 1, okay? When it enters glass, n equals 1.60. So that's n2. That's the object it's entering, okay? So if we want, we can just draw a quick picture to visualize what's going to happen, okay? We have some red light entering at an angle of 13 degrees, not to the surface, to the normal, right? So that's 13 degrees, okay? Now when it enters glass, is it going to slow down or speed up? It's going to slow down, right? So it's going to get sucked towards the normal, I think of it. It's going to bend towards the normal. It asks us to find the direction. That essentially means find theta 2, right? The frequency, what's the frequency going to be? Is it going to change? No, we're still going to have to find it because they didn't tell us it, but it's not going to change, okay? So we'll just say frequency, wavelength, we want to find lambda 2, and we want to find the new speed, so v2, okay? All right, let's just start with a new direction. Might as well, it's the first one they said. So start with Snell's law, n2 over n1 equals sine theta 1 over sine theta 2. Not that you have to remember this because it's on your data sheet, but a trick, okay? All of them are 1 over 2, except for the index of refraction, which is 2 over 1. So if you can remember that that one's 2 over 1, the rest are 1 over 2. So if n2 over n1 equals sine theta 1 over sine theta 2, okay, we can manipulate this where you want sine theta 2. Okay, and then to get rid of n2 over n1, you can do it in 2 steps if you want. I'm going to do it in 1 step. So multiply by n1 over n2. Then n1s cancel and n2s cancel. Just do that to this side. So sine theta 2 equals sine theta 1 times n1 over n2, which equals sine of 13 degrees times n1 is n for air, right? So that's 1 over n2 is n for glass, so that's 1.6. And you get that sine theta 2, be careful here, sine theta 2 equals 0.140594. And then that is not theta 2, that's sine theta 2. So take the inverse sine of both sides. So theta 2 equals inverse sine of 0.140594. Theta 2 equals, I got 8.08 degrees. Okay, so that's its new direction. So theta 2 right here is 8.08 degrees. Makes sense. Always check yourself. Was I expecting this thing to bend towards the normal? Yes, we were. And it did because now theta 2 is smaller than theta 1. So it bent towards the normal. That's good. All right, frequency. So frequency is constant, okay, but we still have to find it because they didn't tell us what it started as. So frequency equals constant, okay, but V equals F times lambda. So F equals V over lambda, which equals, we'll do it in the air because we have both of those things, right? We didn't find the wavelength yet in the new medium. So 3 times 10 to the 8 meters per second divided by 650 times 10 to the negative 9 meters, 650 nanometers. And so I got that the frequency is 4.62 times 10 to the 14 hertz. Okay, and that does not change. All right, lambda 2. So n2 over n1 equals lambda 1 over lambda 2. Okay, so just like before, we want lambda 2, so times lambda 2, boom, boom, times lambda 2. And we still want the wavelength 2, lambda 2, so let's just get rid of both of those things at once. Boom, 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 boom. Okay, and we have that. Hey, look at that. It's the same as before. Lambda 2 equals lambda 1 times n1 over n2, which equals 650 nanometers times n1 over n2, again, is just n of air over n of glass. And I got that it was 406 nanometers. So again, it didn't change colors, okay, because frequency determines color. It did change wavelengths. Okay, last one, which is the whole reason this happened. So it does feel kind of weird to do it last, but the speed. So what's the new speed? Well, according to Snell's law, n2 over n1 equals v1 over v2. Okay, and let's just pause for a second here to kind of acknowledge this is truly Snell's law in its purest form, right? Remember, what are the indices of refraction? They are how much light gets slowed down by a substance, right? So we're saying here that the ratio of the indices of refraction is inversely equal. So N2 over N1 is equal to V1 over V2. In other words, the bigger the ratio of the indices of refraction, the smaller the ratio of the velocities. I'll show the manipulation one more time, but guess what? No surprises here. It's going to look the exact same. Okay, so V2 ends up being equal to V1 over N1, or times N1 over N2. And again, just pause here and look, okay? Think about and again, just pause here to look at what your equation is saying. We're saying that V2, the new speed in this new medium, is equal to the original speed in whatever the old medium was, multiplied by the ratio of the indices of refraction. In other words, divide by the new index of refraction, right? Remember, that's what we said it means. It means that light travels this many times slower in this medium. So if we have air to glass, we're just going, so again, just check your formulas, right? Never just blindly trust them. Say, is what you're saying kind of check out with what I know to be physically true? Which equals speed of light in air is basically the same in a vacuum, because the index of refraction in air is 1. Rounds to 1 anyway, 1.00, I guess technically, over 1.60. And V2 equals 1.88 times 10 to the 8 meters per second. So light slowed down quite a bit by a factor of 1.6, in fact, right? Because that's what the index of refraction means. By what factor will this thing slow down light? Okay, just as a little extra bonus for funsies, if you want, kind of another check that you can do if you want, okay? Now that we have our new speed, V2, and we have our new wavelength, lambda 2, go and check and see if the frequency did stay constant. Use the universal wave equation, V equals F times wavelength, and see if you get the same frequency. You should. Okay, example. Some sort of EMR is in air. This wave is moving at an angle of incidence of 13 degrees. Wow, look at that, same angle of incidence. When it enters steel, N equals 1.70. Now, did you just have a bit of a bruh moment where you are thinking about light entering steel? Well, remember, is all EMR light? No, right? Light is a type of EMR, but not all of it is light. Okay, so how can steel have an index of refraction? Steel can be penetrated by several types of EMR, but for example, X-rays. It's the higher energy ones that can do it. So just a not so subtle reminder, EMR is more than just visible light, okay? So we think about the visible light because it's the one we see, it's the one that's practical for us to use. Well, I shouldn't say that. We use refraction of other stuff too, but it's the one we think about the most. It's the one we can visualize, literally. It's the only thing we can visualize. Okay, will it bend towards the normal or not? Well, remember, if it gets slowed down, it's going to bend towards the normal. If it gets sped up, it's going to bend away from the normal. So if it's entering steel with an index of refraction of 1.7, remember, what does that index of refraction mean? It means how much this substance or medium slows down light, right? So that's actually pretty high. 1.7 is a pretty high index of refraction. So it's going to slow it down. So you bet it's going to bend it towards medium quite a bit. Okay, a thing to be remembered. It doesn't hurt. It's pretty quick to remember it, but no, I guess not. We can use Snell's law to get there, right? So sine theta 1 over sine theta 2 equals N2 over N1. Going to go ahead and jump to the solved version, okay? Because again, it's the same manipulation. And so here, I'll even do it all at once this time. Inverse sine of sine theta 1 N1 over N2, okay? Probably don't do that, honestly, but oh well. Theta 2 equals inverse sine of the sine of 13 degrees times N1 being air again, so 1 over N2 being steel. So I got, when I punched that all in very carefully, I got that theta 2 was 7.6 degrees. So again, this thing bent towards. Good, we were expecting that, right? But if we didn't remember, we could check with Snell's law. And we got that it would bend towards the normal. Okay, what is the effect on frequency? What do you think's effect on frequency? Trick question. Constant, no effect. Okay, what's the effect on wavelength? Well, if it's slowing down, picture ticker tape, if it's slowing down, the frequency stays the same, what does the wavelength have to do? It has to get bunched up more, right? Exactly, just like ticker tape. So the wavelength will go down, it will bunch up. Okay, they didn't tell us the wavelength, so we can't do it numerically, but we can say it went down. And the speed, well, that's what we've been talking about this whole time. Speed went down, right? That's what refraction is. Light bending when it gets slowed down or speeding up, but in this case, since it was going into something with a higher index of refraction, we know it was slowing down. Okay, what actually is going to be the speed? Well, let's figure it out. Okay, V1 over V2 equals N2 over N1. By the way, folks, if you want, flip them both at the beginning. So you know you're looking for V2. You can write it down like this. Just be careful. Flip both sides. Okay. And then some people find this a little bit easier for manipulating. It definitely is, right? Now I just multiply both sides by V1. V2 equals V1 N1 over N2. Some people like that better. I honestly, when I'm doing it, I kind of just start out with them flipped the way I want. If I'm looking for something in the numerator, I keep it the way it is. If I'm looking for something that's in the denominator, the way it's given on the sheet, I just flip it to start out. Okay. Anyway, V2 equals V1, speed of light in air, 3 times 10 to the 8 meters per second. N1, index of refraction of air, is essentially 1. And steel, we've been told, is 1.70. So V2 equals 1.76 times 10 to the 8 meters per second when you punch that all in your calculator. Okay, so yes, light definitely got slowed down. But we knew that before we calculated it. We just were figuring out how much it got slowed down by. You'll notice I didn't fret too much about not knowing the wavelength because I knew the next question was just going to be the same thing, but now giving us the wavelength. Kind of weird that this is 2 questions, honestly. Oh well. Okay, so direction, we did that in the last question. Not going to do it again, obviously. Frequency, hey, we know it's constant. Okay, wavelength, the only thing we couldn't do last time. We did the speed. So now it's just saying EMR has a wavelength of 1.2 picometers, okay? So pico meaning times 10 to the negative 12. If you didn't know that, that's okay. It's on the back of your formula sheet, but that is lambda 1. This wave is moving at an angle of incidence of 13 degrees when it enters steel. What type of wave is this? It asked that first. Okay, remember, there is a bit of memory here. You do need to know this, okay? Pico. As soon as you hear pico, that's gamma radiation, okay? Picometers is very tiny wavelength, very high energy, gamma radiation. All right, let's find the only one we haven't found, wavelength. So N2 over N1 equals lambda 1 over lambda 2. Lambda 2 equals N1 over N2 lambda 1. Again, if you're not okay with how I got there, okay, it's the same manipulation as the last one, so go back and practice that. Okay, N1 is air's index of refraction, N2 is steel's, and lambda 1 is 1.2 picometers, so 1.2 times 10 to the negative 12 meters. That's what pico means. And I got that, lambda 2 equals 7.1 times 10 to the negative 13 meters. Okay, for this one, so think about it. Pause the video, don't let me answer it for you. Which side has the higher index of refraction? So when we say that, higher index of refraction, what are we really saying? We're saying, right, in other words, slows light down more, okay? Or, AKA, if it slows light down more, what does it make it do? Bend towards the normal or bend away from the normal? Right? Makes it bend towards normal. So when we think of it that way, it actually gets pretty straightforward, right? So when light goes from this N1 substance to this N2 substance, did it bend towards the normal this way or away from the normal? When we kind of step back, look at it, you can tell it bent towards the normal, right? This is where it would have gone if it was unrefracted. It's not what it did. It bent towards the normal. So N2 is greater than N1, right? You can think of that as sine theta 2 is smaller than sine theta 1. Inverse relationship between the n's and the sine thetas. Okay, so we kind of saw this in the grade 8 slideshow, right? Where should the hunter aim the spear? Now, this is not the best diagram. We're going to go ahead and say this is where the hunter is seeing the fish. So the hunter sees the fish here, okay? So if the hunter sees the fish here, let's draw a quick ray tracing diagram. Okay, if the hunter sees the fish here, that means there is a ray of light going from here to the fish, to the hunter. Okay, so the fish is not actually there. Now let's think about what light would have done. What would light have done? So the ray of light left the fish, went to the hunter's eyes, but it left the fish, and on the way to the hunter's eyes, it hit water. Okay, so it definitely did leave at this point. The hunter's not wrong about that. What he's wrong about is what it was doing underneath the water. So let's draw in our normal. Okay, so this is our theta 2, right? Now, if it got sped up, it left water, went to air, so it sped up, right? Light went faster. Would it bend towards the normal or away from the normal? If it's going faster, it's going to bend away from the normal, right? I think of it as getting away from the normal, sucking it in. So then that means theta 2 must have been bigger than theta 1. So this means the light must have been bent something like that, right? Because theta 1 needs to be smaller than theta 2. So if that's theta 1, so there we go. We've now made theta 1 smaller than theta 2, okay? So that ray of light shouldn't be dotted really, because it really did travel to his light. We were just using that dotting to figure out what was going on. So this ray of the light really did get bent to him, but then his eye traced it back to see the fish here. So where is the fish for realsies? Somewhere along this trajectory. Real fish versus perceived fish location. Okay, just like this picture shows. So light leaves, it gets sped up, so it gets bent away from the normal, right? Theta 2, clearly bigger than theta 1. Okay, now here's where things definitely get harder than they were in grade 8. I will solve this one. I'm not even going to actually solve the next one on video. I will post the solution in the notes when I post them, but I'm just going to do this one for those of you who want it. Okay, so what is the final position of the ray? So the final Y position. So we're going to have to figure out where it's going to come out on this side. Okay, this is really, though, guys, it's actually not that bad. It's younger math years geometry, and that's all we're really going to do here. Okay, so a little bit of physics 30 and figuring out how it's going to bend, but beyond that, it's just geometry. Okay, so the light will enter here. Okay, and then n equals 1 to n equals 1.3. So is it going to slow down or speed up? It's going to slow down, right? Which means it's going to bend towards that normal. Okay, towards that normal. So what we want to do is figure out where it ends up over here. But before we can do that, we got to figure out what's the new angle of incidence. To figure out the new angle of incidence, we have to figure out the new angle of refraction, right? So you can see we're kind of going to have to shimmy our way across here, angle by angle. These are actually really fun problems. I find them fun anyway. They're kind of therapeutic and fun. So let's go ahead and call that theta 2. It's the first refracted angle. Okay, that's theta 2. So, okay, we'll just go ahead and call this N1, N2, N3. So, N2 over N1 equals sine theta 1 over sine theta 2, sine theta 2, N1 over N2 equals sine of, they told us the angle of incidence was 35 degrees times N1 was 1.0, N2 though was 1.3, and I got that sine theta 2 equals 0.441213, so that theta 2 equals inverse sine of that, which equals 26.18 degrees. Okay, there we go. So now we know this theta. We know that this is 26.18 degrees. This is just a line to make a triangle. I guess it's kind of an extension of the normal. Okay, so if this is 26.818 degrees, this is 90 degrees. Well, then this is a triangle. So we have 180 minus 90 minus 26.18. Okay, and then 90. But then look at this, 90 minus that is just going to give you 26.18 again, okay? You might know also that if you have two parallel lines and a line that kind of bisects them, the angle here and the angle here end up being the same, okay? So there we go. Our theta 2 is also our theta incident for the new one, okay? That's not always the case, but it is here. So we will call that theta 3, just to avoid confusion. Theta 3 equals 26.18, okay? So then let's say now N3 over N2, because now we're passing out of here into here, N3 over N2 equals, sorry, I got ahead of myself. We got to draw our diagram. Okay, so now this refracted ray is going to get refracted again. Now, is it going to go slower or faster in this new medium? It's going to go even slower, right? It's x of refraction once again. Okay, so I'm bending it even more. Okay, So this is going to be, let's call this tiny angle here. Okay, we'll call that theta 4. So n3 over n2 equals, oh geez, if this could be more confusing, equals theta 3, the first one, over theta 4, the new one. Okay, 1 and 2 just means old and new. New over old for indices of refraction equals old over new for everything else. Whoops, not theta, sine theta, sine theta. Okay, so manipulating that, you will get that sine theta 4 equals n2 over n3 times sine theta 3. And so theta 4 equals inverse sine of n2 over n3 times sine theta 3 equals inverse sine of n2 over n3 is now 1.8 over 1.3 times sine of theta 3 we just found to be 26.18. Okay, and I got then that theta 4 equals 18.58 degrees. Okay, so that is the angle at which it comes out. So we can draw another triangle here. Okay, and there we go. Why are we drawing these triangles? Well, what we're asked for is to find the final y position. So how do we get that? The final y position is wherever it comes out relative to where it started. It started at y equals 0. So this is essentially the whole point of the question, right? That's the whole point of the question. So it would have taken this trajectory if they all had the same end, but you can see it got bent forward. It got bent towards the normal so much a couple times that it ends up, well, taking a pretty different trajectory by the time of all is said and done. So let's go ahead and call this A, and we'll call this B. And then if we call this Y, then Y equals A plus B. Okay, so the triangles, why are those helpful? Well, now tan of theta 2 equals opposite A over adjacent, which is this purple line. How big is that? 5 centimeters. So A equals tan theta 2 times 5 centimeters. A equals tan of 26.18 degrees, 2.458 centimeters. Okay, and then moving now to this triangle, well, tan of theta 4 equals opposite B over adjacent, which is again just 5 centimeters, right? B equals 5 centimeters times tan of theta 4 was 18.58 degrees. And that means B is 1.681 centimeters. Okay, so Y equals A plus B, so Y equals then 2.458 centimeters plus 1.681 centimeters. And that means that the final Y position is 4.139 centimeters, or 1 sig dig actually is all we can use because they give us 5. Okay, 4 centimeters. Okay, that wraps up topic 3. If you're looking for practice, check the Google Classroom or the agenda for which ones go with this.